Hello, Woodstock chemistry students. Here is the last little bit of chemistry lesson that we need to do for the year. We need to double back to looking at nuclear reactions, which got covered in student presentations, but I don't think we ever really kind of pushed ourselves to a deep understanding. So let's focus today a little bit on nuclear reactions. We've talked about fission and fusion, and today's lesson is really going to focus on fission, the splitting apart of nuclei. Just so you know, both fission, certainly fission, not fusion, but fission is occurring naturally. It's part of what we might call our background radiation. It's something that we live with every day, and radioactive elements within the Earth's core actually help to keep the Earth's core heated. It's happening all the time, and it's just something that we live with. Both fission and fusion wind up releasing energy according to the E equals mc squared law, as the mass of the products, which are often called the daughter particles, is slightly less than the mass of the reactants, which are known as the parents. And this is a little bit counterintuitive, as you'll see when we take a close look at the parts of the atom that exist both before and after the nuclear reaction. There are three kinds of fission reactions: alpha, beta, and gamma, but that's a little bit misleading in that in every single case gamma radiation is produced. And so you'll see right here there's a gamma ray that's coming out of this parent particle. This is plutonium, I think. Well, I'm not sure, but I think it is plutonium. Nevertheless, here's an image of an alpha decay event, and gamma radiation is being released. So what's happening with an alpha decay? Well, a large parent particle will produce a small particle, which was historically referred to as the alpha particle. We'll come back to that in a moment. And then a larger daughter, in this case uranium-236. This uranium-236 is typically an unstable atom, and it may go through its own alpha decay in some time, but that's just part of what happens often with large nuclei, is that they are just inherently unstable. It's called an alpha particle because it always emits this little combination here, a small nucleus that we later learned was indeed the helium nucleus itself. With an atomic mass of 4, you see it's got 2 protons and 2 neutrons, so it's got an atomic mass of 4, and an atomic number of 2 because it has 2 protons. You'll notice that the number of atomic, the atomic mass seems conserved. You've got 236 protons and neutrons from the uranium and 4 from the helium, and together that makes 240 from the original parent particle. You have 94 protons, 92 in uranium, 2 as helium, so it looks like the number of protons is preserved as well. So despite the fact that when you add everything up and just simply count protons and neutrons, there doesn't seem to be anything missing, a really important piece is this, that the mass of the daughter particles is indeed less. If you put these two pieces on a scale, a really sensitive scale, they wouldn't weigh as much as the original parent particle when all the parts are kind of bound to one another inside the nucleus. It's a little bit odd, and I won't get into that right now. It would make this a half-hour discussion, but it's some missing mass, and that missing mass goes into the form of the gamma ray, which is the energy that is the result of the missing mass, which gets multiplied by c squared. So if we go back here for a second and highlight this, the missing mass between the daughter and the parent, the daughters and the parent, that missing mass gets converted into energy. So a little bit of missing mass can create a lot of energy because it's being multiplied by c squared. So that's the story with the alpha particles, alpha decay. It always emits an alpha particle. Ernest Rutherford and his team, including a fellow named Hans Geiger, who created the Geiger counter, and the Geiger counter actually counted the number of helium, or what they called alpha particles, that were being emitted during these sort of spontaneous decays of these large nuclei. So for a long time it was called an alpha particle, in that it was the first kind of emitted particle that we saw from a nucleus. Later, when we got to look at it more carefully, we understood that it was always a helium nucleus. Okay, let's take a look at the next one. The next type of decay is called a beta decay. In fact, there's kind of two versions of it. We'll walk through what's called the beta minus decay, and there's the symbol for it, beta minus, okay? With the beta minus, the atomic mass is unchanged. So here's our example. Cobalt will undergo a beta minus decay into nickel, and in the process it will emit an electron, an antineutrino, and some gamma ray radiation. Okay, this particle here, the electron, is called the beta particle in this reaction, and that's the thing that might be detected most easily by any sort of nuclear detector. So what's happening? The cobalt-60 is made of 27 protons and 33 neutrons. When it undergoes this beta minus decay, it becomes nickel-60. So you notice that the atomic mass hasn't changed. What has changed? Well, we've picked up one proton and we've lost one neutron. In fact, a neutron has become a proton. So in here, one of the neutrons has transformed itself through some mechanism which we'll talk about another time, has transformed itself into a proton. So we've moved up the periodic table by one. We're now at nickel, but charge has to be conserved. So the fact that the nucleus is now more positive because a neutral item became positive, that has to be balanced out. So a negative particle, in this case an electron, gets shot out of the nucleus. This is not an electron from the shells of nickel. This is an electron from deep inside the nucleus that is being rejected by the nucleus and shot out at a fairly high speed. It's a very odd thing that has happened. Gamma ray radiation is produced again. All these particles here, the electron, the antineutrino, and the nucleus, the nickel itself, weigh less than the original cobalt-60. It's worth talking about the neutrino or the antineutrino here. There's a tremendous story about how Wolfgang Pauli presented or proposed this idea in the mid-1930s. Scientists thought that energy might not be conserved during nuclear reactions, or that momentum might not be conserved during nuclear reactions. Pauli thought these were very, very fundamental laws that must be obeyed. So, though he couldn't detect it, he proposed that there be a little neutral item that would leave the nucleus and carry away some energy and some momentum, and therefore conserve both of those. That was in the mid-1930s. It took about 20 years before physicists could measure the neutrino and detect it. And during that time, mostly people had such great faith in the conservation of energy, conservation of momentum, and Wolfgang Pauli that they believed it was likely true. They just didn't know how to detect it. Now we detect them all the time. Very interesting particle. Briefly, I'll try to describe the beta plus decay. In this particular case, again, the atomic mass is unchanged. We have 10 protons plus neutrons here, 10 protons plus neutrons there. In this case, one of the protons has become a neutron. And so we move down in the periodic table from number 6 to number 5. We've emitted the neutrino, and again, to conserve charge, since we were at this positive charge has sort of gone missing from the nucleus, it gets carried off in this anti-electron, which is also known as a positron. And once again, gamma ray radiation is emitted. The last of the three is the one that is in some ways the simplest. Some large nuclei. Here we are, we're back with this plutonium, 240, very large nucleus. They're very unstable and they're kind of jostling around. You can imagine this collection of protons and neutrons just kind of oscillating back and forth, vibrating back and forth, crashing into one another somewhat, moving around inside here, quite unstable. Every now and again, large nuclei like this will just settle down into a lower energy state and not change their composition, but just rather their arrangement, and in the process give off a gamma ray electromagnetic wave. Okay, no change in the mass or the atomic number. Okay, those are the three types of decay. There's a practice page that looks like this, and I'm asking you to consider carbon and what would happen to it when it undergoes a beta minus decay. Then oxygen, what would happen to it as it goes through a beta plus decay, and so forth. So use your periodic table to identify the atomic masses and atomic numbers of the parents, and then write out what the outcomes will be if they go through these particular, oops, got a typo here. If they go through these particular, there we go, these particular radioactive decay modes. Okay, good luck.